The last part is going to plot the reflectivity spectrum of an DBR. So it's actually combining the part of the reflectivity of Bragg's condition and the reflectivity of arbitrary combination, because when you design your Bragg's condition for specific wavelengths, it's actually an arbitrary combination for other wavelengths. So let's consider this scenario. We already designed our alternating layers specifically for the breadth condition for a given wavelength. Yeah, here. So the L1 will be lambda 0 divided by 4n1, and the L2 is lambda 0 divided by 4n2. However, we are trying to obtain the reflectivity of the wavelengths not equal to the designed wavelengths. So as long as we trying to plot the reflectivity with all available the lambdas, then we get its reflectivity spectrum. All right. In order to make the notation cleaner, we introduce some new terms. Basically, it's just a combination of the known terms. The first is period, period or the periodicity. Large, it is gamma or lambda, large lambda. Okay, the high capital, the capital lambda in Greek later. So basically, this is just the summation of the two thickness L1 and L2. Second, it is called the average propagating constant beta, or we can have the beta bar arbitrary. Because we want to know, we want to see the two layer with one. So we'd like to mix the two property together. So we just assume the average the propagating constant times the whole the period should be equal to beta 1 L1 plus beta 2 L2. Alright, so the beta is actually, you can divide it to the other side. So the beta will be L1 divided by gamma, which means L1 plus L2, and L2 divided by gamma, something like that. Alright, and with average the propagating constant, we referred it to an average the refractive index. So after comparing the equation from both sides, you will obtain our average refractive index as a half of n1 minus n1 inverse plus n2 inverse, then inverse it again. So it's something like a geometric average, and yeah, a little bit like, but not exactly. Okay, so then we further introduce a term called the detune. Yeah, because it's already designed for a specific wavelength. So for that specific wavelength, it refers to beta 0. But now we are trying to know the reflectivity about the arbitrary wavelengths. So we define the difference in the wave vector as the detuning. So the delta, small delta, lower delta will be beta minus beta 0. So it will be 2 pi n. N is the refractive index. That's neglect the possible effect of the index dispersion first. So let's assume we have a common average and common average refractive index. So it will be 2 pi n bar times 1 over lambda minus 1 over lambda 0. And for simple notation, we also define the number called the effective number of period. That's because we know that for one pair, this is the reflectivity of one pair. And the tangent m lambda is the reflectivity of m pair. So, effective number of pair, that means that it's like if the reflectivity is small, so the reflectivity, the power summing up for every pair, like one pair, two pair, three pair. So reflective number of pair is just thinking things like is how many pairs equivalent if we only assume the power summing ups, yeah, for each little interface. So although this number is not going to infinite because the reflectivity at most is to be 1, but when the R1P is small, it will be closing to the actual number of pairs if the M is finite. So in this case, we just in order to make this term a simpler way, so we just call something like the pair number of period. So we denoted MEFF. Actually, you don't need to take the physical meaning of MEFF too seriously. You can just imagine it is a way to simplify the further equation. Okay, and another term is called the generalized detuning parameter, which means you obtain the matrix element for one pairs, and to evaluate like how much it is away from Bragg's condition from another perspective. Because if under Bragg's condition, T22 will be T21, we have already showed that, but if it is not, it will be the T22 and the T1 will differ. So if higher the T22 minus T11, you will get a larger detuning. Yeah, so it is purely intuitive. You might ask why we need to introduce two tuning parameters. And the tricky way to answer is that the second term, generalized term, is also only for simpler notation. But we have a more another explanation that because while you are trying to build a alternating matrix, it doesn't need to be a Bragg's condition for specific wavelengths. It could be truly arbitrary. But for a really truly arbitrary combination, it could be also some high reflectivity combination for some reason. Although it is not designed by lambda over for n, but it still be it could still be constructed interference. So in this way, probably it is not the degree of detuning. It is no more, but defined by a perfect Bragg condition. Yeah, it's not applicable now, but we can still observe how much the detuning is by the difference between the T22 and the T21. Yeah, if for some specific combination of the L2 and the L1, and you can find the delta generalized detuning, yeah, could be it is small for specific wavelengths. So you could still build up a high reflectivity by such means. Okay, so this is a rather more general explanation what is the generalized detuning parameter. But in such case, in this case, we are not going that far. We are just to discuss the detuning of a designed Bragg's condition with different wavelengths. So now we just took the upper delta here as a way of notation simplification. Okay. Alright, so how do we obtain the reflectivity of a black mirror with arbitrary wavelengths? The procedure is just the same. We'll just repeat trying to obtain the reflectivity with G with the TG21 and the TG11. But we want to link this expression with the terms with Bragg's condition like MEFF and the delta, something like that. Yeah, since these values are from Bragg's condition, with lambda 0, and this is arbitrary result or generalized result. Lies the expression. Okay, so the path to link both is also purely mathematical. So I will just tell you the sequence of rearrangement is that the first you got RG of TG2, TG21 and the TG11, and the TG21 and the G is here. First, we can substitute all hypersign as hypercosine times hypertangent. Okay, this is the definition of hyperbolic functions. Then second, we replace this term tangent m cos c divided by tangent cos c with a term MEFF, effective number of pairs. Then finally, we replace the rest of the hypercosine cos c, which is 1 over 2 T11 and the T22. And if you compare this term with the definition of generalized detuning parameter, you will see it should be T11 divided by 1I delta. Yeah, which the large delta is the generalized detuning parameter. So the whole procedure is line by line is here. So since I don't want this to be a math class, if you want, you can just take a pause and take a look at one line by line. You will get the same result as I described in this page. Okay. 3, 2, 1. Yeah, long enough for you. Okay, so now we got the TG11 as 1I MEFF delta times hypercosine m cos c, and the TG21 is blah blah blah, something like this one. And finally, this is R1. R1 means the reflectivity of one pair. Reflectivity of one pair DBR, and times how many effective pairs, and times 1J and the delta hypercos m action. So the final expression is TG21 divided by TG11 will be R1 times MEFF times 1I delta divided by 1 plus I MEFF delta. So if you can take a quick look, if there is no detuning, means at the exact wavelength detuning, then delta goes to 0. So the second term goes to 1. So the RG is still R1 MEFF. Yeah. And we know that in this case, R1 will be hypertangent and MEFF is the hypertangent and divides hypertangent yeah, it will reduce to the expression in the first section. But what we are more interested when the delta is not zero. Obviously, we will see you will obtain an complex value. Yeah. The RG is a pure real value only when delta is zero. But in when there's a detuning, the reflectivity becomes an imaginary number, and we will try to describe how it looks like with a different amount of delta. All right. So to tackle that, we will start with the phase 5 plus minus for the arbitrary scenario, which will be beta 1 L1 and the beta 2 L2. Alright, since now the wavelength isn't the exact the breadth wavelength, so the beta 1 can be written as the exact wavelength with detuning. Yeah, since we already defined the lambda is the beta minus beta 0, so the beta is the beta is replaced with the beta 0 plus is the detuning. Okay, and under breadth condition, the beta 0 times and the gamma is, we know that each layer gives a half of a pi phase delay. So beta 0 times gamma is pi, and the rest is the delta times, so two at both of them are delta. Yeah, okay, delta lambda. Oh no, second is lambda, so it becomes delta lambda. Okay, so this is the term of the 5 plus, and the 5 minus is the negative term. So, and since we let it be beta to be lambda of arbitrary wavelengths divided by 2 pi n1, since we assume the dispersion is small, it is reasonable because we are not trying to obtain the reflectivity with a very broad range. So that's just assume the n1 is still n1. It's the same with the n1 at breadth condition. And the L is the lambda 0 divided by 4n1. Alright, so same for the second term. So after terminating the common terms, yeah, it is still 2 pi lambda 0 divided by, pi lambda 0 divided by lambda divided by 2. So this is lambda 0 and over lambda times half of pi, same as this, the second term. So it should be 0. Okay, so we put this to the generalized grating, and you can compare the expression in the previous pages. So the case of the one pair T11 becomes 1 minus 1 divided by T squared with exponential I delta lambda plus R squared. Yeah, you just see that we have 4 elements everywhere. So the reflectivity for one pair is the same for T21 divided by E211. We have an R times exponential I delta lambda plus 1 divided by exponential I delta lambda plus R squared. Okay. When does the R1 become 0? It becomes 0 when this term becomes minus 1. So delta lambda to be pi. Delta lambda to be pi, then so it will be and the AR condition if the wavelength is half of the breadth wavelength. But this is not precise because in half of wavelength, the reflecting index will be pretty different. So this is not the point of the interest now. Okay, what is interest is when the wavelength is close to the designed base wavelength. So let's see what's the what happens with multi-tuning. So now we have the delta like this and the T21, T211. With such expression, we will see the delta can be further simplified as this, since T22 minus T11 will be T22 minus T11 will be minus T squared over 1. The T22 is exponential minus I delta lambda plus R squared, then minus exponential I delta lambda plus R squared. Okay, so both leave this term, and it becomes T squared over 1, and then we put the minus sign in, so it becomes exponential I over delta lambda minus exponential I delta lambda. Then we can divide the 2 outside and put times the 2 here. So it becomes T squared over 1 over T squared times, this is a definition of the sign, and delta lambda with, okay, so I have I here, so it will be something like this. So this is the T22 minus T21. And for the T22 plus T11, it becomes the minus, okay, let me change the color. So for the T22 plus T11, it is T squared over minus 1 with common R squared twice, and plus exponential I delta lambda plus exponential minus I delta lambda. Okay, so we can put this divided by 2, then times 2 again. Okay, so it is T squared over 1 times, okay, we can just pull out minus 2 directly, and it is R squared plus cosine delta lambda. Alright, so when times I inside, it become minus 1, and eventually you will get the result. You can double confirm that. And when the delta lambda is small, this term close to 1, or it should be close to 1 minus delta lambda square. Yeah, if you do the Taylor expansion, divided by 2 plus R squared. Since this term is small compared to R squared, so we can just neglect that. And the sign delta lambda will be delta lambda. Okay, so the delta lambda, where the absolute value of the generalized detuning, also happens with the detuning in wavelengths.